Hi, welcome back. In this video, we're going to talk about attributes of quadratics. An attribute is really just another word for characteristic. So we're looking for things that make a quadratic special and unique. We're going to dig into some vocabulary words, so make sure you have paper and pencil ready. Let's get started. Alright, so here, under quadratic attributes, we're going to start with the very first vocabulary word, and it's really what another word for calling a quadratic is a parabola. It's a parabola because it follows this shape, and that's actually what this is called. A parabolic shape is when it changes directions like that, more like a U-shaped curve, right? It can be pointing up, or it can be upside down and pointing down. So a parabola is really just another word for a quadratic. Now, one of the most important, or one of the first important attributes of a quadratic is known as the vertex. The vertex is this point right here of the quadratic. Let's see if I can write that. This point or this point. So we call it a vertex because it's going to be either the lowest point of the graph or the highest point of the graph. Another word for this, lowest point and highest point, would be called a maximum or a minimum. So if we have the lowest point in the graph, as we see on the right side, we call this a minimum. Or in shorthand, we can call this the minimum value, because it's the smallest value of the graph. Or if it's upside down, then we call that point in the graph the highest point in the graph, or the maximum. Also known as the max. So the vertex could be a minimum value or a maximum value, but that is where the graph changes directions. If it's pointing up, it's going to go downward, and it's going to reach the vertex where it shifts directions. The reason why the vertex is so important is because it's sort of like the middle of that parabola. It's what's going to help you divide this parabola into equal parts. Notice how we have this dotted line here on both sides, the upside down one and the one that's pointing up. That dotted line is known as the axis of symmetry. The axis of symmetry can also be expressed as, for short, the AOS. It's called the axis of symmetry because it divides the parabola down the middle through the vertex. It cuts it in half like an axe. The axis of symmetry is what keeps the parabola symmetrical. So whatever you see on the left side of the graph will always be symmetrical to the right side of the graph. Whether that's pointing down or whether that's pointing up, the axis of symmetry will always go through the vertex, and it will symmetrically cut it right down the middle. Okay? And the axis of symmetry will always go through the vertex. It's always going to go through this x value. So if you see here, it's going to go through this point right here. And in this scenario, the axis of symmetry would be at x equals 2. Whatever that x value is on that vertical line that it touches, right, that's going to be the equation of the axis of symmetry. The vertex is an actual location, so we can call the maximum the minimum. We can give it a point. We can put x comma y as the vertex. That's how we would label the vertex. All right, let's talk a little bit more about what makes a quadratic so special. Okay, so now let's talk about the x and y intercepts. Let's start with the x-intercepts. Now there's several ways of calling it an x-intercept, but the x-intercepts is where it's going to intercept the x-axis. So if you look here on the x-axis, call this the x-axis, this is the y-axis. These 2 points are known as the x-intercept. So here we have an x-intercept at x equals 6, and here we have one at x equals -2. You can write it as an x equals, or you can write it as a coordinate point, 6, 0, or -2, 0. Now, x-intercept is one of the words that we could use. There's actual 4 different words we can use to refer to an x-intercept. We can call it the roots. We can call it the zeros. I'm going to use a 0 for that. And the reason why it's called a 0 is because if you notice here, the y value on the x-axis will always be 0. So we're looking for the zeros. We have roots, we have zeros, we have x-intercepts as a word. And the last word we use is also solutions. You can think of these 4 words as nicknames for the same concept. Just like you get called by your name by your friends, a different name maybe by your parents, a different name by your aunts and uncles and relatives, and even maybe a different name when your mom's upset that you haven't done something, right? They're all the same person, which is you, just using different names to refer to it. And that's what we do here with roots: zeros, x-intercepts, and solutions. You can remember this with the acronym of ROX. R-O-X-S. Those are the 4 possible ways we can refer to an x-intercept. For the y-intercept, we're now referring to where it crosses the y-axis because it intercepts the y value or the y-axis in the graph. So this point right here would be considered the y-intercept. And in this case, it equals y equals 3 or 0, 3. Now the x value is 0 and the y value is 3. Now when we're talking about x-intercepts or solutions, as we see here, right, solutions is another word, there are 3 possibilities. A parabola can have up to 3 different ways of intersecting the x-axis. First, it could be like your general form, like the one that we just drew right now, where it crosses the graph twice. And if you see here, we have 2 x-intercepts or 2 solutions, one here on the left and one here on the right. Even if it's upside down, it can cross twice, right? We can also have one solution, and that happens when the vertex is right on the x-axis. So let's say that it's here, and the vertex itself, the minimum, is going to be on the x-axis, so it only touches it once at the very, very bottom. One x-intercept. And then there's also the possibility where the graph doesn't have any solutions, right? When it has no solutions, it means that it never touches the x-axis, and maybe it's just somewhere up here. It never crosses the x-axis, so there's no x-intercepts. So these are the possibilities. You can have 2 solutions, 1 solution, or no solutions, no real solutions. Let's talk about our last characteristic of a quadratic for now. This last one is the domain and range. Anytime that we talk about a function, we talk about the domain and the range because this tells us where it's possible that it can exist. The domain is very straightforward. Let's just draw a picture here for domain. Let's say we have a general picture that looks like this. So I can draw it better. Because we have 2 arrows, one pointing to the left and one pointing to the right, all x values on the graph are going to be possible. This arrow on the right is going to continue infinitely to the right, which means the graph can exist. You just have to zoom out some more. And on the left, because the arrow goes to the left, this graph will also continue to exist. You just have to zoom in more. So when we're referring to domain, the domain of a quadratic will actually be all real numbers. And we can use this symbol, this R with 2 lines, to refer to all real numbers. Which means all numbers are possible. Negatives, positives, decimals, fractions, whole numbers, integers, all real numbers are possible for the domain. The graph will always exist on the left and on the right. You can also refer this as x could be anything between negative infinity and positive infinity. Those are the options. The range is a little different. The range does have limitations. If we think of the range, I'm going to see if I can use a different one. If we look at the range, now we're looking at the y-axis. So domain refers to the x values, the input. The range is the output. If we're looking at the y value on this line, now there's not everything is possible in this scenario, right? Notice how the graph does exist up here. Oops. The graph does exist here in the top, but it doesn't exist down here in the bottom. The graph doesn't even go down there. So the range is actually going to be based on the vertex, the minimum or maximum value. We'll start with this example as a minimum. So what we do is we look at the minimum value. Here we have 1, -4. All right, the minimum value is -4, the lowest y value that's going to exist. And because it's pointing up, we say that the range is going to be everything above that -4. So whenever you have whenever the graph is pointing up, it's going to be everything higher than that value. We just have to find the value, the y value, and say everything greater than that -4. Now, if the graph is upside down and it's pointing backwards, let's say we have this scenario. Let's say that we have, give me a second, an upside down scenario. Now it's not a minimum, now we're dealing with a maximum. Say that we have something like here. The domain is still from -infinity to positive infinity because there's two arrows. There's an arrow on the left and an arrow on the right. But now because we have a maximum, this point right here will be the highest value. This point at -3, will be the maximum value that the graph will reach, which means we cannot have any y values existing above the maximum value. There's nothing up here in the graph. Everything is below this value. So we find the y value, which is 3. Right? And we say it's everything below it or everything less than the 3. So you're going to be focused on, for the range, we're focused on the y values. Identify the y value, and is it everything above it or is it everything below it? The domain is always going to be all real numbers. The range is the one that you have to pay attention to the vertex. And are we going up above or are we going below? Let's do a couple of examples where we identify all of these attributes and we see what things look like and put this to actual use. So here we have a graph, right? And this graph, our goal is to identify all of the attributes or characteristics that we just spoke about by looking at it. If you're given an equation, you can go to the equation, put it in the calculator, and then identify it. You can analyze the graph through those settings. But looking at this graph, there's a lot of things that I'm interested in. I'm going to start with this in the top. What direction does it open? It opens upward. Now, because it's opening upward, this point down here, what do we call it? Is it a maximum or minimum? Is it the highest value in the graph or is it the lowest value in the graph? It's the lowest value in the graph. So we call that vertex the minimum. And then we look at that vertex. What's the location of that vertex? Well, that vertex happens to be at 0, -4. So the vertex and the maximum and minimum are always going to be connected, right? Now let's look at the x-intercepts, also known as the roots or the solutions. We have one here on the left, and we have one here on the right. And both of them are at, one of them is at -2. So you can put -2, 0, and the other one is at 2, 0. The next question here is referring to the AOS. The AOS is another acronym for axis of symmetry. Remember, the axis of symmetry is like an axe that symmetrically divides the graph down the middle. So where is it going to cut it in half? It'll always be through the vertex. What's the x value, right? Where does it touch the x-axis because it's a vertical line? Where does it touch the x-axis where it cuts the parabola down the middle? And it cuts it right at 0. So x equals 0. Whatever x value it touches on the x-axis, where it's in the middle, that's going to be your AOS, your axis of symmetry. As for the y-intercept, we're looking for the y value. Where does it cross the y-axis? This also happens to be the vertex. So the y-intercept is also the vertex. And that is going to be at 0, -4. And finally, we're down to our last two attributes, the domain and the range. When you're looking at the domain, because we have two arrows, right, we have one going to the left and we have one going to the right, all x values are possible. So you can say x is between -infinity and +infinity. Or you can say x and this fancy symbol epsilon, and then two double lines with the r. What that means here is that it's saying x is a subset or is the set of all real numbers. Epsilon is just another Greek letter that we use in math to say x is the set of all real numbers. The range. Finally, let's look at the range of this graph. Now this is dealing with the y values, the y-axis. We're going to look at the graph and we're going to find the vertex every single time. That vertex is the thing that we're looking for. So we're looking for y equals -4. Now, is it everything above -4 or everything below it? Because the graph is going upward, it's everything above, which means we're saying the y value can only exist when it's everything greater than or equal to that -4. And that's pretty much it, guys. If you have not subscribed already, click the subscribe button. Click the like button if this has helped you in any way. And as always, we'll calculate later.